Hello and welcome to today's lesson where we shall be discussing the concept of topology and topological space. Definition: let X be a non-empty set and let tau be the collection of subsets of X. Tau is said to be a topology on X if 1. X and the empty set are elements of tau. 2. The union of any number of sets in tau belongs to tau. And 3. The intersection of any two sets in tau belongs to tau. Now the pair X tau is now called a topological space. So to define a topology, we need two sets. The first set is X and set X must be non-empty, which means that set X must contain at least one element. And the second set is tau, and tau is nothing but what? Is a collection of some subsets or all the subsets of set X. Now if we have these two sets we've just defined, and these three conditions here are satisfied, the first one is that the set X and the empty set must be elements of tau. Second condition is that if we pick any two union or any finite or infinite union of members of tau, the result should also be in tau. And finally, if we intersect any two sets from tau, the result should remain in tau. If this happens, then we say that the collection tau is a topology on the set X. And if tau is a topology on set X, then we'll bring X and tau together as a pair. We now call this pair a topological space. We'll now take an example to clarify the concept of topology. Example 1. Let X equal the set with elements A, B, C, D, E, F, and tau the set with elements X, Phi, A, C, D, A, C, D, and B, C, D, E, F. The question is this collection tau a topology on the set X? What do we observe here? The first thing we observe is that set X is a non-empty set. It contains how many elements? 1, 2, 3, 4, 5, 6. It contains 6 elements. Therefore, set X is non-empty. It satisfies the first condition. The second condition is that we define the second set tau, and tau is a collection of subsets of X. Let us see. X is the whole set, and of course in set theory, the set is a subset of itself. The second element here is Phi, and Phi means empty set. An empty set is always a subset of a set. We have A, we have CD, we have ACD, we have BCDEF, BCDEF, and these are all subsets of set X. A point to note: these elements of tau are called open sets. Open sets. The elements of the non-empty set X are called elements of X, while the elements of the collection tau are called what? Open sets. We want to now investigate if this collection tau is qualified to be called a topology on the non-empty set X. To do this, we verify the conditions given in the definition. The first condition says that X, the set itself, and the empty set must be members of the collection tau. Let us see if this is true. So we go to tau and check. Is X a member of tau? There is X here. We've seen that X is an element of the collection tau. We now check again. If the empty set is also in tau, we check. Phi is here. The empty set is also an element in tau. So we have seen that the first condition is fulfilled, that the set itself and the non-empty set both belong to tau. So X and the empty set are members of the collection tau. So the first condition of our definition is satisfied. We now go on to check the second condition. The second condition says that the union of any number of sets in tau should belong to tau. Let us check this out. Let us pick X and Phi, for example. So if we have X union Phi, what do we get? Now the union of a set and the empty set is nothing but what? The set X. So we picked two open sets from tau, and we have checked their union. What's the union? The union is what? X. And is X an element of tau? The answer is yes. X is in tau. So X is an element of tau. Let us pick another pair, another two open sets in tau and check again. Let us pick CD and ACD. So if you pick the set CD, the open set CD, union the open set ACD. Let us check the union out. What will be the union? The union will be A, C, and D. This is the union of these two open sets. Now the result we have is ACD. We now check, is ACD a member of the collection tau? We check. ACD is here. So ACD is also an open set in tau. So ACD belongs to tau. We check another, let us check another two pairs. Let us check these two. Let us check ACD union B, C, D, E, and F. If we take the union of these two open sets, what do we get? We get A, B, C, D, E, and F. We get A, B, C, D, E, and F. And what is A, B, C, D, E, and F? This is nothing but what? The set itself, X. And the set X is also in tau. So this open set we've gotten, which is the union of these two open sets from tau, is also an element in tau. And if you go on and pick any other two open sets in tau, you discover that their union will always be an element of tau. Therefore, our second condition of definition is also fulfilled. We now go ahead and check the third condition before making a conclusion. The third condition says that the intersection of any two sets in tau belongs to tau. Let us check this out. 3. Let us use this same open set to check the condition. The first one, let us check the intersection of X and the empty set. And what would that be? If we intersect a set and the empty set, what will be the intersection? The intersection is what? Empty, because they have nothing in common. Now, the intersection of these two open sets gives us phi. Is phi a member of the collection tau? The answer is yes. So phi is a member of tau. Let us take another two open sets. Let us take these two here. If we take again the open set CD, intersection, the open set ACD. Do we get any intersection? Let us see. CD and ACD, there is something in common. C and D are common to both sets, to both open sets CD and CD. The next question is this open set a member of the collection tau? We check. CD is here, CD. So CD is also a member of what? Of tau. Let us check again using these other open sets. So if we take ACD intersection, the open set B, C, D, E, and F. Let us check if there's anything in common. We have A, we have B, C. What is there? C is common, as well as what? As well as D. So once again, C and D are common to both open sets. And CD, once again, is an element of tau. And indeed, if you take any other two open sets from this collection tau, you observe that the result is also an element in tau. So what do we conclude? Since this subset, this collection tau, satisfies an X, satisfies the three conditions of our definition of topology, we now conclude that what? That this collection tau is a topology on X. And we can now write that X with that collection tau is what? A topological what? Space. Let us take another example. Example 2. Let X be the set A, B, C, D, E, and tau be the collection with open sets X, phi, A, C, D, A, C, E, B, C, D. Question again is this collection tau a topology on X? Like we did in the previous example, we have to investigate if the collection tau satisfies the three conditions that makes tau a topology on X. The first condition is that the set X and the empty set must be elements of the collection tau. Let us see. Obviously from tau, X is here, so X is an element of tau, and we see again that the empty set phi is an element of tau. Therefore, the first condition of our definition is fulfilled. We now move to check the second condition. The second condition says that the union of any number of sets in the collection must belong to the collection tau. Let us check this out. Let us pick the first two, X union phi. If we take the union of a set with the empty set, what will be the result? The result is nothing but what? X, the set itself. And is X a member of tau? The answer is yes. X is a member of tau. So this is satisfied. Let us pick another pair and see what happens. Let us pick CD and ACE. So if we pick the pair, the open set CD, and take the union with the open set ACE, what do we get? The union of CD and ACE is simply A, C, D, and E. We will now check. The open set ACDE, is it a member of the collection tau? We check. ACDE is not a member of the collection tau. Since the open set ACDE, which is a union of the two open sets CD and ACE, is not a member of the collection tau, we check no further. At this point, it is safe to conclude that the collection tau defined this way is not, so tau is not a topology on the set what? On the set X. And so we cannot call the pair X tau a what? Topological what? Space. So I hope you understand what a topology now is, as well as a topological what? Space. As an exercise, you have a non-empty set X with elements A, B, C, D, E, and F, and you have three collections here defined. The first one is tau 1, tau 2, and tau 3. And these are the open sets in tau 1, open sets in tau 2, and open sets in tau 3. This is F. The question is, which of the following subsets, which of them is a topology on X? And you justify your answer. So leave your answers in the comment section below, and do not forget to subscribe to this channel. Thank you, and bye-bye.